Here. So today on A Place Called Space, we are going to talk about exoplanets. Exoplanets. So these, what are they? They are planets that are around other stars, right? So I've got Jupiter here and Neptune here. These are the most abundant exoplanets that we found, are things that are like Neptune or that are like Jupiter, orbiting other stars outside of our solar system. When you look up in the night sky, you see tons of stars, right? So many stars. So there's got to be exoplanets, planets out there. There's got to be thousands of them out there that just might have life. How cool would that be to find another Earth-like planet that has another species like us? You know, that would be extraordinary. Now, let's see. When we look up in the night sky, how many stars do you think there are? Yes, so there are 100, 200, 300. So it depends where you are, right? If there's a lot of light around you, or if the moon is really bright, it's harder to see the stars when you look up because there's so much light going on. But if you were able to get rid of all of the extra light and look far out into the solar system, beyond it, into the galaxy, beyond the galaxy, into the rest, using different telescopes, you would see that there are over 1,000,000,000,000,000,000,000 stars. That's 1,000,000,000,000,000,000 stars. How many is that? That's a really big number. Here we go. I wrote it down for you because it's so large. Let's check this out. So, billion, trillion. So that we got a 1 with how many zeros after it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There are over this many stars, a 1 with 22 zeros after it, in our entire observable universe. So observable means as far out as we can see. So it takes time for light of a star to reach us. So like our sun, when it has light, it takes 8 minutes from the sun that's in the sky to come in. So if I open this window real quick, it took 8 minutes for that sunlight to come in here and touch my face. So stars that are way out far away, it takes a long time. So we've only been able to see about 14 billion light years away. So that's our observable universe, and that's how many stars we think are in there. So let's compare it to something. There are more stars in our observable universe than there are grains of sand on all of Earth's beaches. That's a lot. So if you go to the beach and you scoop up sand, there's millions of little sand particles in there, right? You dump your hand out, the sand comes down. All of the beaches on Earth, there are more stars in the sky than grains of sand on Earth's beaches. I love that. That's so cool. You look up, there are so many stars. Now, unfortunately, where I live here in Los Angeles, we can't see too many stars. But when I go camping, that we get away from all the lights of the city, you can look up and you can see a bunch more stars. And sometimes even you can see the Milky Way galaxy. So all those stars up there, we think almost every single one of them has a planet around it. So that's what our exoplanets are. Now, how long ago did we find our first exoplanet? The first one that we found was in 1992, right there, 1992, and it was what we call a hot Jupiter. That's this thing right here. So we call a hot Jupiter a planet that's around another star that's kind of like Jupiter. But what we call hot Jupiter is normally it is closer to its star than Jupiter is to our sun. Because in the beginning, when we saw that, we're like, how is this possible? How can a Jupiter-sized planet be that close to a star and go around the star in like 4 days instead of the long time it takes for Jupiter to go around our sun? So it baffled us for a while. So the first one was in 1992 called a hot Jupiter. Now, it's cool to find exoplanets, right? But we want to find ones that are like Earth. It's back here. That are like our world here to see if there's aliens out there. So move this up. It was 1995, which we found our first Earth-like planet. So we say Earth-like to mean that it is in the habitable zone. What does that mean, habitable? It's kind of a big word, right? How about this? Goldilocks. If you've ever heard of the story of Goldilocks, So she was laying in a bed that was too hard, then she found a bed that was too soft, and then she found one that was just right. And then porridge that was too hot, porridge that was too cold, and then she found porridge that was just right. So the Goldilocks zone, or the habitable zone, is the right amount of distance that a planet is away from a star. So we've got our giant sun here. Earth is in the right spot where it's not too hot, it's not too close, and it's not too cold. It's not too far away that liquid water can pool on the surface and be okay. If it was closer, it would evaporate. The oceans would boil, boiling water, eventually it all goes away. There'd be no more water left. It'd be like Venus or like Mercury, too hot. And if we were a little bit further away, it would be too cold. So you see how we have the North Pole and the South Pole with ice? All of Earth would eventually turn into a giant snowball, and it would be too cold for us to live if we were just a little bit further away. So the Goldilocks zone, the habitable zone, is that right area and distance that a planet is from its host star, so the star that it orbits, to be considered Earth-like and habitable. So when we're looking for exoplanets and we're looking for aliens, we're trying to find ones like Earth, because that can tell us that, hey, there's a better possibility that there's a civilization. There's life. By life with a civilization, it means it's smart. It can think, and it could maybe look for us. It could be like, hey, we're pretty smart. We know things. Maybe there's other things out there that are smart like us. So if we're looking for a planet like this, maybe they have the people, aliens, whatever we want to call them, that are there trying to look for us as well. So these are the ones that are really interesting for us to find. Now, we've been looking for exoplanets for decades. We found the first one in 1992. We found this first Earth-like one in 1995. So we've been doing this for a long time, for almost 30 years. So how many exoplanets have we found over that period? Well, thousands. There's a lot. We have found 4,141 exoplanets confirmed as of yesterday. NASA has an ongoing clock that tells us it's a counter, not a clock, a counter that tells us every time a new exoplanet is found, adds it to the list. So as of last night, we were over 4,000, and they have another part of that counter that says like candidate exoplanets, which means we're not exactly sure if they're real or if it's other things in the data, but there's over 5,000 of them. So if all of them are real, add it to this, that's almost 10,000 exoplanets that are out there. There's gotta be one that's got aliens, right? I mean, there's so many things out there. There has to be something with aliens. I mean, I hope so. I think that maybe there are aliens. The only thing is it might not be right now. So Earth and our solar system have been around for about 4.5 billion years. And our species, humans, like Homo erectus being able to do all this stuff, has really only been around for about 200,000 years. And then our universe, observable universe that we know about, is about 14 billion years old. So it's a lot of time, and we're just a tiny little blip in that timeline. So maybe way, way, way back when, there was aliens that were like us, maybe even smarter, but then they're not around anymore. Something happened. Kind of like when the asteroid came and extinct the dinosaurs. Maybe that happened to some aliens way before us. Potentially, they might be out there. So we've got over 4,000 exoplanets. Now, how many of them are those hot Jupiters, those Neptunes? We have a super Earth variety, and then our Earth-like ones. How many? Let's break it down. Let's figure out how many of those exoplanets of the 4,000 are like Earth, because that's the exciting part. Well, we're going to start with our Neptune. See, the exoplanet's trying to get away from me. So our Neptune exoplanet, I'm going to start, they're all on this piece of paper. We've got 1,388 of those 4,000 are Neptune-like. So that means they're like ice giants. Okay, that's a lot of them. The next most abundant thing we find is the hot Jupiters. The hot Jupiter is like a gas giant, 1,302. That's how many of those we have of the 4,000. Now, super Earths, So a giant version of Earth, we've got 1,284 super Earth. So it's a little bit bigger than Earth. Could potentially be in the habitable zone. Not exactly sure. And then we got the Earth-like ones. There's only 161, which only that's a lot of them, right? But Earth is rare. I mean, we got 8 planets in our solar system. We haven't found anything that's slightly resembling to this close to us. So 161, not that many, but that kind of makes sense because we're really special. And then we have 6 of them here, 6 that are unknown. We've detected an exoplanet, but we're not exactly sure what type of exoplanet it is. So first we find it, then we have to analyze all of the data to see how big is it massive, what's the density of it, and we can do all of that with telescopes. I'm going to tell you in a little bit which telescopes we use to hunt for these exoplanets, but we got to hunt for them, right? So how do we hunt exoplanets? Good question. What is the closest exoplanet to us? So we're here on Earth, right? We're around our sun here. So the closest star to us is Proxima Centauri, right? So most of those stars have planets around it. So closest star to us, Proxima Centauri, which is 4.25 light years away. How far away is that? Well, 1 light year is 6 trillion miles. So if we take 4, we'll round down from 4.25 to 4 times 6, that's 24 trillion miles away is that star. And it does have an exoplanet around it. It does have an Earth-like exoplanet around it. And that is Proxima Centauri b. It's not that creative of a name, right? Proxima Centauri b is the Earth-like planet that is the closest to us. So the closest star to us also has an Earth-like planet around it. So that is over 24 trillion miles away. Now, let's talk about this. How long would it take us to get there? So the fastest thing we have in the solar system right now that we've built is called Solar Parker Probe. So that's a satellite, that's a spacecraft. That's a satellite that's going and it's going to like touch the surface of the sun. And it's traveling the fastest thing so far, 430,000 miles per hour. It's flying. So if we were going 430,000 miles per hour and we need to go 24 trillion miles, we're going to figure that out. One second. Got my marker. Check some math. Let's do this. Okay. So we got 24 trillion miles. All right. And then we got 430,000 miles per hour. Carry the 2. And that is, okay, I did this before because I knew that question might come up possibly because I wanted to know because I didn't know. It's 6,372 years. The fastest, 430,000 miles per hour for 24 trillion miles. It's going to take us over 6,000 years to get there. That is forever. Like that's just not possible with current technology. We'll work on it. We'll maybe get there one day. But first, we got to figure out how do we hunt for these exoplanets, right? So we're hunting for exoplanets. We're out there. We're searching. We got like telescopes. Well, this is a binocular, so a telescope is the one. There we go. How do we find exoplanets? Well, there's 4 ways to do it. All right, 4 ways. There's a new one that's been used pretty recently that I'm going to tell you about at the end. The first one is the easiest way. Let me grab my sun. So here's our star. Now the first one is called the transit method. This is the easiest way because we have found 76% of our exoplanets using this method. So what is it? So transit method means that it is in our direct line of sight. So let's say Earth here is the planet, right? And you, let's say we'll make it a little easier. You are Earth, right? You looking at me right here. You're Earth. Here's the planet. Here's the star. So you're going to sit here and you're going to look at a star. You're going to look at a star, look at a star, look at a star. And you wait until a planet passes in front of the star. Okay, so the light coming off the planet goes down just a little bit because the planet blocks that light. So the planet comes, transits in front of the planet and blocks some of that light. It's called the transit method. It's easy. It's just coming around and blocks the light. Now, let's do a little demo of this. Got a flashlight. Boom, ba-doo-doo-doo. So if we have the flashlight here, and where is my planet? There it is. Here's my planet. Okay, so here it is. We got the flashlight is their star, and then the planet comes. See how it blocks the light? Right there, we're blocking the starlight, and the starlight dims a little bit, and then it comes back. So as we're staring at a planet, we're staring at a star, waiting for a planet to come, boop, block some of that light, goes down, and then as it goes, the brightness comes back. Now, that means that the planet has to be right in our line of sight. So if the planet was orbiting, let's bring this back, like this around the star, right? Then we wouldn't be able to detect it this way because it doesn't block out any of that light. So the transit method, it has to go in front of the star, block the light, and keep on going. And that's how we figure it out. Now, second method, that's 4, 2. Second method is my favorite method, and it is called the wobble method. All right, wobble. What does that mean? Well, give me 1 second. I've got an assistant, a friend here to help me out. So we look at a star in the night sky, all right, and it's wobbling back and forth, all right? So we see here, see there's Jupiter over there? So Jupiter does this to our own sun. It causes our sun to wobble. And you're like, why? Well, Jupiter's so big. It has so much mass, right, that it pulls on the sun a little bit. And by pull on the sun, I mean that they both orbit the same point. So our sun is moving back and forth, right? So there's a middle point between these two that is the center of mass. So if you're on a teeter-totter and it's teeter-tottering, if you weigh the same as your friend, it stays in the middle. But if you weigh more, it tilts. So the middle part of the mass between the sun, which is huge, and Jupiter, which is our biggest planet, is right here, right off of the surface of the sun. So the sun orbits around that point. So if you're looking at it like this, it's going to be wobbling because Jupiter's pulling it. So when we look in the night sky with telescopes and we see a star wobbling back and forth like this, we know that there's a Jupiter-sized planet pushing or pulling on it, making it wobble just a little bit. And in the beginning, people just thought there was something going on. Maybe the star was getting like brighter and like not as bright, brighter and dimmer. But then we're like, no, let's look at that a little bit more. All right, it is wobbling because there is a star around it. So that's called the wobble method. It's the second way we find planets. And it's found about 19% of our planets so far, our exoplanets. It's wobbling. So cool. We're just looking for stars to dance. They're dancing out there. All right, thank you, Jupiter. Appreciate it. Now, third method. So really recap. Transit, 76%. Right, the wobble, 19%. Now, this one's tricky-ish. Say tricky-ish. It's called microlensing, and it accounts for 2% of the planets we find. So what is microlensing? The audio went down again. I'm sorry. So, see, so we did the wobble. So we have our star that's way in the back here. So if two stars align, the first star turns into a magnifying glass to look at the back star. So we've got two stars that align. It's called microlensing. And that first star turns into a magnifying glass to help us magnify and see the star in the back. And then we can find the planets around it. So it's two stars that align. The first one turns into a magnifying glass so we can look at the star in the back and find planets around it. So now this next one, the fourth way that we find exoplanets is called imaging. Imaging, and this gives us 1%. Now, what is imaging? Well, we can actually take pictures of exoplanets, but it's really, really hard because the starlight is so bright. So, got my star here again. if I want to look at a planet, let's say it's right here, right off of the star, but the starlight is so bright, it's hard to see that planet because it like drowns it out. So what we do is when we take a picture, we block out the starlight. So you see, this is on my camera and it goes right in front of that. See how all of the light is blocked? Now I can see the planets around it without having the starlight drown it out. If there's too much glare, we block the starlight and then we can see the planets around the star. So that's the fourth way. We've got transit, wobble, microlensing, and imaging. Someone just said, no, that doesn't add up to 100%. That's 99% because it's like 76.2, 19.8. It's around there roughly about how many percentages is to find these planets around other stars. Now, we're hunting for them with our telescopes. Which telescopes? So right now, the three main telescopes we use to hunt for these exoplanets are right here. We've got the Hubble Space Telescope, the Kepler Telescope, and then TESS, which is the Transiting Exoplanet Survey Satellite. TESS, that's what it stands for. Because Hubble and Kepler were named for astronomers. They were named for scientists. And then TESS is an acronym, Transiting Exoplanet Survey Satellite. These are the three main telescopes that we use to hunt for exoplanets. But we want to hunt for more. So we got more coming up. The James Webb Space Telescope is launching next year in 2021, and it is going to be the new exoplanet hunter. And we're going to learn so much more about our exoplanets, and we're going to look at the atmospheres of those exoplanets to see, are they atmospheres like us? Do they have oxygen, which can only come in an abundance from life? That's one way that we've determined if there's aliens on these exoplanets, would be like there's potential for life if there's a lot of oxygen in the atmosphere. And then WFIRST is another one that's going to launch in 2025. This is going to help us look for exoplanets as well as looking at dark matter. Dark matter, it's an unknown thing. We've got matter, and then dark energy in our universe. So WFIRST is going to help us look for exoplanets and also dark matter, but that's a long time off in 2025. So many cool things about exoplanets. Let's see what kind of questions we got from you today. I see some that are over here. Closest exoplanet to us, the Proxima Centauri b. Hubble Space Telescope has helped us find a lot. Is there an express way to a wormhole to cut down like the commute? Possibly. So like gravity is the bending of space-time. So if we can figure out how to bend space-time, we can drop that commute. But right now the speed limit is the speed of light. So if we're going straight there, it's going to take us, over 6,000 years to get to that planet. Very nice. How do we know how far away the closest Earth-like planet is? Well, with telescopes. So we look in the night sky and we figure out where are the closest stars, and we can tell a star is closer to us or further away from us by how the light shifts from the star. If it's shifting towards blue, it's like coming towards us. If it's shifting towards red, it's going away from us. So we're able to determine how close stars are based upon the light shifts. And then whichever ones are the closest, we then find the planets around those, and that's how we find the closest Earth-like planet. All right, let's see. Boom, boom. Got it. Here we go. Yep, and then the 100%. So there we go. There with that, that is our exoplanets today. And I'm going to talk about this. So right here, this is a cool poster. So this is a poster. PSO J318.5-22. Kevin, why are you showing this to us? Well, there's exoplanets that aren't around other stars. What? So they're called rogue planets. And this is one that we found where it's a planet without a star. It's just a rogue planet. It's out there that we found. So then we made this poster at NASA that says where the nightlife ends because there is no daylight. So you don't need to have a star to find a planet, but it's a lot harder to find rogue planets than it is to find planets that are around other stars. That's the easier version. So we have transit, wobble, microlensing, and imaging to find our exoplanets. Thanks for tuning in, everybody. Hit the like button. If you like this video and you enjoyed what you're learning today, make sure you click subscribe so you can get alerted when these new videos come out. And I'll see you again tomorrow at 9 a.m. Pacific time to learn more about space. Thanks, everyone.